So for our word problem example, here it tells us that it doubles, right? The action that's taking place, that is your y equals a times b to the x. That action right here, that's your b value. So you know that b is doubling. So how do you represent numerically that something's doubling? Times 2. So you know that your b equals 2. Then it says the initial concentration is 1.5 million bacteria per milliliter, okay? When it says initial or beginning or starts at, that's a key sign that that's your A value. So for this problem, our A value is 1.5 million. So it says find a function that gives the concentration. Well, our function would be y equals 1.5 times 2 to the x. I like to put my exponential in parentheses just because me and my decimals look weird. Along with my multiplication dot. That is not a 2, Shauna. 2. So that's our function. So then it says estimate the concentration after 4.5 days. So if we have f of 4.5, we're just going to plug that in. So we have 1.5 times 2 to the 4.5. Now, was that a terrible word problem? No. No. It's just about reading and knowing what you have. So then I'm going to go to my handy dandy calculator. Yep, calculadora, and get it done. Okay, so in here, I'm going to type in 1.5 times 2 to the 4.5. So after 4.5 days, how much bacteria is there now? 33.9 million bacteria. 33. Oh. My pen did that on its own. Sometimes it gets a little funky. 0.9 mil. Oh my gosh, you really want me to write out more? Million. Is that better? Million. Okay. So again, the hard part, quote unquote, is reading. And then once you read, you can write your formula, your function, whatever you may need. And then you're done. Okay. Questions about a word problem with exponential? Huh? Take it off the calculator. All right. Now, exponential function as a transformation. So when you have an exponential function, you have 3 variables in total, not including x and y. You have A, B, C, and D, correct? A is our reflection or stretch or compress. Do you remember that? A always has that same role. C tells us whether we go left or right. And remember that our x's are liars, okay? Our D, that's our down and up. And then things to remember, all of the domain are going to always be all real numbers. Our horizontal asymptotes depend on our D value. Therefore, our range changes depending on our D value. So if our D is anything other than 0, then our asymptote and our range are going to be also affected. Oh my goodness. Have y'all noticed that our transformation rules don't change, right? A stretch or compress, or reflect. C, always with X the liar, right or left. D, up or down. Those rules will not change, okay? Are we still writing? Are we good? Okay, so let's look at this graph. So we have 2 to the x plus 1, okay? So with 2 to the x plus 1, just to look at it, we have our C value, agreed? And even though C looks like it's a positive 1, it's actually a negative 1 because our x's are liars. So we know that C equals negative 1. What that means as far as this table goes, we're going to look at our parent function first. So our parent function would be based off of our original. So our original was negative 1, 0, 1. So we would be at 1/2, 1, and 2. So that's the parent function. This is our PF. So when I graph this, if I want to graph 2 to the x plus 1, C is affecting my x value. So to each x value, I have to shift it to the left 1 unit, which means that I'm adding a negative 1, right? So plus negative 1 for U. I wrote that so backwards. So plus negative 1, plus negative 1, plus negative 1. So now all of my values have been shifted. So there's my asymptote at y equals 0. Why did my asymptote not move? Is there a D value? No. My asymptote will only move if there is a D value. And do I have a D value? No. So my asymptote isn't moved. So my new x values would be at negative 1 plus negative 1 is what? Negative 1 plus negative 1 is negative 2. So at negative 2, I'm at a half. Negative 1 plus 0 is negative 1 plus 0. Negative 1. So at negative 1, I'm at 1. And then negative 1 plus 1 is 0. So at 0, I'm at 2. Guys, I'm kind of pretty proud of my little curve right there. Now the end, don't judge, and that would be your function. And that song's even older than Jump. All right. So just going through here is just going through different ways. The main thing, then there's another analyzing, compound interest. If you plan on going into business, finance, economics, any of those fields, this will be one of your most commonly used formulas. It's the compound interest formula, and it works like this. Yeah. So you have your amount, your principal, your rate, the number of times the interest is compounded per year, and then your time in years. How long is it going to go? Okay. It's just a formula that you would utilize, and I guess we will model that on, what's that day called? Monday.